hello to everyone who watches in the recording. So today we are going to continue where we left last time. If I remember right, we discussed at the end of the last lecture, we discussed a little bit about how domain influences the questions of where the minimum of a function is located. As in, for example, here you remember we found that domain depends on here I guess domain is doesn't change the location of the minimum, right? No, yeah, here is for example the example where domain actually allows the function to even have a minimum, otherwise because it would have been infinity. Here we discussed that in the absence of boundaries we cannot define a minimum of this function. It can goes towards both plus and minus infinity, the solution, as the function can decrease infinitely in both of those directions, and so on, right? So we saw that domains could be bounded, finite size, infinite size, and ultimately the solution can lie at the boundary of the domain, same as at the point where derivative of the function is equal to 0, right? Okay. We saw last time also what else did we see? We saw that whether or not minimum of a maximum exists also depends on the domain, like same domain but a different minimization versus maximization makes a difference. All right. Now of course finally it's the last detail is we saw that strict inequalities when we do convex optimization are suspicious. The convention is to only use non-strict inequalities. All right, that was the last lecture. Now let us move straight into the battle. We'll go into the new material. So domains can be what we call convex. Okay, they can be convex. What is a convex domain? Well, that is quite intuitive from the name. Convex domain is a domain where you have each pair of points, and let me show it here. Each pair of points, let's say one point and another point, can be joined by a line, and the entire line segment, right? The entire line segment would also lie inside the domain. Okay, so that is the definition. So any 2 points, you can choose another pair of points. Let's say a point here at the edge. You can connect them with the line, and the entire line will lie inside the domain. That is a convex domain. Non-convex domains are the ones where you can find such a pair of points where the line would stick out of the domain. Like here, for example, I found the line where part of the line segment, where part of the segment does not lie inside the domain. So the figure 2 shows you non-convex domain, figure 1 shows you convex domain. Just as one sort of fringe example, I can show you those 2 points. They are connected by this line here. Notice that this line is actually a boundary of the domain. But the boundaries, as we started to talk in the previous class, are part of the domain. We prefer to deal only with non-strict inequalities. So with domains like this, we can assume that the boundaries are in the domain. In fact, later when we will discuss what a convex domain is, we'll more or less assume that the boundary is always included in the domain. Okay. So this is a practical assumption. The boundary is part of the domain. So we can connect any two vertices, and you would get the edge of the, like in this 2D case, right? You'll get an edge which is part of the domain. So figure one actually shows you a convex polytope, but that is of course not the only example of a convex domain. So let me just quickly, using what Zoom allows us, I'll show you other types, just a couple. For example, this is a convex shape. So ellipsoid, convex, any 2 points would lie inside. Of course, something like this is convex, right? Circle, the disk is convex. Now, just a couple examples of non-convex domains. For example, something like this is non-convex because I can draw a line. Let me show you. I can draw a line like this. Part of the line sticks out, so non-convex. What are other non-convex domains? Well, for example, something like this is non-convex. You can see already where I can draw a line which would stick out. So this is non-convex. All right. But it's also interesting that this is also a convex domain because any 2 points on this domain, like we can choose point, we can choose 1 point, another point. You can connect them with a line, line segment. It will be inside the domain. So a line itself is a convex domain, or a line segment is a convex domain. All right. So convex, if on leaf for any 2 points, the line segment connecting them is also in the domain. Questions? We have questions about it. No questions. All right. Now, when you try to prove that, let's say, domain is convex or non-convex, it is very useful to use the idea of a convex combination. I apologize for the noise. This will be better. So it is convenient to remember that for any 2 points, x1 and x2, all points in the line segment connecting them. So let me actually start drawing so you can see what we are talking about. So x1, x2, right? There's x1, this is x2. So all points in the line segment connecting them. So we are talking about now this line segment here. All points on this line segment can be expressed as alpha x1 plus 1 minus alpha x2, where alpha goes from 0 to 1. So if you want to discuss any points on this line segment, you can always just pick a alpha that you like, and you would get, if you pick alpha equal to 0, this is where you are. If you pick alpha that is 1, this is where you are. If you pick alpha that is 0.5, you'll be here. 0.25 here, etc. So varying alpha, it works as a slider. Your solution goes from here to here. So your point XL on the line segment. Okay. So all the collections of points on this line segment is given by this expression, alpha x1 plus minus 1 minus alpha x2. And this expression is called convex combination. So we can say convex combination of those 2 points is, etc. So this is a convex combination, this expression here. We'll use it quite a bit. That is a standard terminology, so I suggest you remember the term. Okay. Any questions about convex combination? Okay. Okay. Now let us see. So some examples of convex domains. So for example, if X is Rn, that is a convex. That is convex. So Rn, space of vectors, n-dimensional vectors, is a convex domain. How do you prove it? Well, you can say that any linear combination of two n-dimensional vectors is an n-dimensional vector, so it is inside the domain. So you can prove that any, this is convex. Right. This thing, what is it? Well, it is a space of all vectors x in Rn, where element-wise each x is less than h. What do you mean element-wise? Well, it means x1. Let me write it here. So it means x1 is less than or equal to h1. X2 is less than or equal to h2. Less than or equal, I just write it as less, but we don't use strict inequalities here, so it is always non-strict, etc. So how does this space look like? Well, in 2D, I can show you pretty easily how it looks like. So again, let me demonstrate. Here's a two-dimensional plane. Let's say H is given by this blue point over here. Let's say this is H. So what are X which are less than or equal to H? Well, first of all, in terms of horizontal axis, we can instantly see that every X which is on the left of this line would be on the right of this line would be not allowed. So in fact, like all of this is out of the question. Those are bigger than h in terms of horizontal axis. All right. Now, in terms of vertical axis, you can draw this line, right? Draw this line. And then you can say everything that is on top of this line is bigger than h in terms of vertical axis, okay? Everything on top of this line will be bigger than x in terms of vertical axis. So the solution, what we are looking for, is actually this space that is, defined here. Like this is the solution. Okay. And now, okay, this is a solution. So this is what we are looking for. Can I prove that this convex? Oh yeah, sure. Take any points, any 2 points here, and connect them with a line, and just prove that the line has to lie inside. How do I do it? Well, I would do it algebraically, not geometrically. So, right. So what I want to prove is that from the fact that, let me show it to you carefully. From the fact that x1 is inside this domain, so x1 is less than h, and x2 is inside this domain, so x2 is less than h. It follows that that this guy would be inside the domain. Okay, that's what I want to prove. So first I start by multiplying x1 less than h by alpha. Good. Then I multiply x2 by less than h by 1 minus alpha. I can do that. I multiply on both sides. Nothing happens. Those are positive coefficients. So the inequality doesn't flip. All right. But since now what we have is this, right, is less than, let me show, is less than this. And also this is less than this, we can point that the sum of the first two is less than the sum of the second two, right? So it's like two small number, like if, yeah, right. The sum of this and this would definitely be smaller than the sum of this and this, since component-wise they're also smaller. Oh, that's what we get. But this whole expression here is nothing but h, right? You can open the brackets and you see alpha h plus h minus alpha h is h. So we just proved that this guy is less than h. And that's what we want to prove. So we proved that this region is convex. We're not going to do it very often, but I just wanted to show you that it is possible to prove those kind of things. Do you have any questions? All right. All right. Okay. Okay. Now, another example. Let's say we have domain in R2, which is defined as x1 squared plus x2 squared less than h squared. So in fact, there's a circle with the radius h. It is convex. Let's just try one more time to prove something. So this is the same as saying norm of x is less than h. So again, what we want to prove is that convex combination of x1 and x2, any x1 and x2 in this domain, would be less than would be by norm less than or equal to h. So inside the circle. All right. Do you understand what I mean when I say inside the circle? Let me just quickly demonstrate. I think this is one of those things where demonstration helps a whole lot. So we have a circle, radius h. What we are trying to prove is that if x1 and x2, both of them are inside the circle, so they're like this is 0.0, okay, center of the circle, 0.0. So if both of those numbers, their norm is less than h, then any kind of linear combination those two numbers would have would also be by norm less than h. Geometrically, it is completely clear. Now let's try to prove it algebraically. There probably is somewhere a theorem in geometry, but we can just prove it again. So first of all, we can multiply, since x1 by norm is less than h, then alpha times x1 by norm would be less than alpha h, right? Scaling the vector with the scalar. Okay. Next, what we can do is we can do the same thing as x2, but multiply it by 1 minus alpha. Good. The norm of this linear combination, and that's what we want to prove, is less than h, would have to be less than or equal to the sum of the norms of those two vectors. Why? Well, this is one of those fundamental theorems. It says vector 1 plus vector 2, the norm of those two vectors would have to be less than or equal to the sum. The norm of the sum of those two vectors would have to be less than or equal to the sum of the norms. Yeah, it's related to those theorems about the triangles and so on. Like the sum of the length of two sides would have to be less than or equal to the length of the other side, etc. Those things. All of those like just kind of fundamental ideas in vector spaces, etc. So, all right, so we use this fact here, and then what we can do next is we can let me get some color. So we can observe that this guy, which is here on the left, is element-wise less than this other guy. So what do you mean element-wise? Well, this guy is less than this. Why? Because, right, we just proved it before. This guy is less than this. Why? Oh, here. And again, this whole thing is just H. Open the brackets so we get. So this is how we prove that this is a convex domain. Those types of proofs look tedious, but they're actually relatively easy. Relatively easy. Any questions about this proof? All right. Now, was there someone? Oh, sorry. So now for another domain, another convex domain. So let's say we have X in Rn, and our domain is all X such that X transpose AH, HX is less than or equal to 1, where H is a positive definite matrix. Well, this is also a convex domain. In fact, what it describes is a ellipsoid. Is an ellipsoid. This is an ellipsoid. Okay. How do we prove that it is a convex domain? We're not going to do it too much. Let's just do it kind of like, do a little bit of the proof. If such a thing even exists. Okay. For any positive definite symmetric matrix, you have this decomposition. So you can always decompose it as d times d, where d is called the square root. I think we already discussed it once. So you have this decomposition. Okay. Now, with that, what we can do is we can say that this can be rewritten as this. So far, so good, almost the same. Now we can define y as dx. Y can be equal to dx. Then the domain, the original domain here becomes d minus 1 times y, okay, d minus 1 times y. And this becomes y times y. Right. Okay. So what is this? What is this? Well, now we can see what it is. It is a unit circle here. So this is a unit circle. Y squared less than 1, unit circle. And this unit circle is being deformed by the matrix D inverse. What do you mean deformed? Well, we get a unit circle. Let me draw it here. Imagine you have a unit circle, and then you apply a linear transformation to it. What does linear transformation do? Well, linear transformations usually rotate, stretch, and rotate. Where does this come from? Rotate, stretch, and rotate from SVD. Remember what SVD does? Any operator can be represented as its SVD. So SVD is U times sigma times V, right? I'm not putting transposes here. So what does it mean? Well, V and U are rotational matrices. They are orthogonal, orthonormal even. So they only rotate, and sigma is a diagonal matrix, so it only stretches. So in fact, every transformation first rotates, then stretches, then rotates. So what will happen to this thing? First it will be rotated, which will do nothing. Then it will be stretched, and then it will be rotated one more time. So result might be something like this, so it can be more orientated different ways. But yeah, so this is an ellipsoid. This is an ellipsoid. Yep. And since you know that, how to prove its its convexity. Well, what you can do is you can say, okay, you know that on the for in terms of y, this is convex, right? Like this domain, unit circle is convex. It is just that it is later stretched, right? And that's it, right? You can any 2 points on this unit circle, the line connecting them would also be inside the unit circle. And then everything else is stretched, but straight linear transformations do not make non-convex things convex. By the way, which is also something you can prove. You can prove that domain cannot become non-convex after being deformed by linear transformation. That is an interesting thing to try to prove. Alternatively, much easier, you can say, okay, give me x1, x2, give me a line between them. Then you transport everything into y by using this thing here. You change your x into y's, and then you just test it against this condition here. That's it. Well, also easy enough. You can prove the convexity of this thing. You don't have to, though, but you can. Geometrically, I think it is clear that they are convex. Any questions about this example? About the fact that it is ellipsoid? Right. We'll come back to ellipsoids often enough. So it's not something you'll be able to forget. Okay. Now, some examples of non-convex domains. Well, for example, this guy is a non-convex domain. Why? Well, because it looks like this. Let me show you. It looks like this. So from -1 to 2, and from 3 to 7. So there is a gap. So you can pick a point here and a point here, and the line connecting them wouldn't lie inside the domain. So this is not convex. Another one is this expression. This is kind of like a unit circle, but the domain is everything outside the unit circle. So if you want to try to draw it, it will be something like, here's a unit circle on the the plane. Just move it a little bit. But the domain is everything that is outside the unit circle. So domain is something like all of this, right? All of this is domain. And you can clearly see that this domain is not convex. Why? Because you can easily pick 2 points. Again, you can pick 2 points. Let's say this point here, this point here. The line connecting those 2 points would happen to lie contain something that is inside this units h circle with a radius h, and this already makes it non-convex. So this is how you can prove that it is non-convex. Actually, when you prove non-convexity, all you need to do is to just show that there is at least one point that is a linear combination of 2 points in the domain, which is not in the domain. That's all. You just need to show one point. Same here. This is the same as before, but it is outside of like everything except the ellipsoid. That kind of domain. Again, non-convex. This is non-convex. Do you have questions about those examples? Okay. Now, we need one more thing. We need a definition of what it means to be convex function. Convex domains, we understood. Okay, good. Now we need to one more thing, convex functions. Function is defined so we have a function f of x defined on domain D. So now we have domains, we talk about them all the time. So a function is defined on domain D. If for this function, it is true that for all x1 and x2 in the domain, the function of the linear combination, so the convex combination of x1 and x2 is less than or equal to the convex combination, same convex combination of the outputs of this function, then it is called convex. I think this is almost always makes you like, like what? It looks very ugly. Like this expression is just takes the whole line very big. But let's see what it means. Geometrically, it is actually very simple. Geometrically, it's very simple. So here are x1, x2 in the domain. Okay. Now, all of this are the values that the function takes when you input convex combination of x1 and x2 into that function. So I'll color code it this way. So green is this line. Okay. I would even try to like draw over it. Right. So the green is the function output when the input is a convex combination of x1 and x2. It's just part of the function. So you just slide x between x1 and x2 and you get this function. Okay. Now, red on the other hand, red, that is a convex combination of the outputs. If we call, if we decide to call, let's say, f1 is equal to f of x1, and we can say f2 is equal to f of x2, then red will be convex combination of f1 and f2. So this part, right? Or if you want, we can say this this is f1, this is f2, this is f1, this is f2. Okay, and the red is the convex combination of those two. So what we want is for the function itself to be smaller than the convex combination of. Yeah, we want the function to lie under this line. But in mathematically, it means the function output, if the input is a convex combination of the x1, x2, should be less than the convex combination of the f of x1 and f of x2. Okay. Linguistically, just horrible no matter how you put it. I mean, maybe someone can put it better, but it's very difficult. But visually, though, I think it is extremely clear. Extremely clear. You have a function, you connect any 2 points on this function. You want the function to be below those 2 points. So, for example, this function is not convex because you can find 2 points where part of the function, namely this part, sticks above the line. What you want for a convex function is for the function to be under the line, completely under the line. That's what you want. Okay. So this is the situation. The convex functions suggest functions that are less like under this line. Under the line that connects would be under the line that connects to outputs of the function. Okay. And you can meditate on this for a while. Maybe it would become clear, or maybe it's already clear. I don't know. It's hard for me to say. I think this is not something that is very difficult to get, but it is just annoying to look at. As in, this expression is just huge. That is a problem. Okay. Okay, let's just move to the examples. I think it will be clear. So this is a convex function. Why? Well, geometrically, it's very clear. This function looks like this. It is just a horizontal line. You can take any 2 points on this function, right, here and here. And the convex combination of those 2 points would not stick on top of this function. So it is convex. By the way, before we continue, let me just address one thing. We have this word concave in the English language, concave. We use it in optimization too. Concave is the opposite of convex. So concave functions, for example, would look like convex functions looks like this, okay? So they would stick always under any combination of the 2 points. Now, concave is opposite. They would always be on top of any combination of the 2 points. Okay. Non-convex does not mean concave. Concave and non-convex are not synonymous under any circumstances. Okay. What is interesting, though, lines and all linear functions are both concave and convex, because when we say the function should be under a combination of 2 points, we say under or equal. When we say the function should be on top of a combination of 2 points, we say on top or equal. So linear functions are always equal. On a line, you can put 2 points, connect them with the line will lie on the line, so, of course. So they're both convex and concave. All linear functions have this property. Okay, now this, again, what is this? This is again a linear function. That function looks like a line, looks like this. You can see instantly that it would be convex and by the way concave as well. This one, same, but scaled up. Again, concave and convex both. This again, both convex and concave. All linear functions are convex and concave at the same time. Now, difficulties start when we start to think about quadratics. Is this convex? Can someone tell me? Is this convex?
Yes, convex.
How does
Yes.
that? How can we tell? How can you tell?
So when you there is only one minimum for this.
Mm-hmm. But how do you tell it is convex and not concave, for example?
We take differentiation twice.
Okay, that is like deep knowledge. But that is deep knowledge from I think something like introduction to optimization or something like this, right? Or advanced calculus, something from there. Good, very good. Yeah, but if you want to check it using our definition, it would be a little bit difficult, right? You would have to prove essentially that what are you going to prove? You have to prove that x1 squared times alpha, right? Plus that is a function. So this is a convex combination of the outputs of the function. Plus 1 minus alpha times x2 squared. This have to be bigger than alpha times x1 plus, let me give myself more space, plus 1 minus alpha times x2 squared. This is how ideally you should prove it. You should prove that this thing is smaller than this. That is ideally how you would want to prove it. And of course, you can open the brackets here. You would find that, the terms would be very similar, except here you would have a lot of a squared. A is less than 1, so a squared would be less than a. You'd also find that You would have terms with x1 squared, x2 squared on both sides, but you would also have x1, x2 with a minus sign, etc. So you would find a way to prove it, but it is annoying. So difficult. But geometrically speaking, it is again extremely simple. Geometrically speaking, what you're talking about is a parabola. Connect 2 points of a parabola like this. The line that connects 2 points would always lie on top of the parabola. So that's the way to prove it geometrically. Of course, it's not rigorous because what did you do here? But at least visually, not geometrically, visually it is very clear. All right. What about this guy? Do you think it is convex or concave? Or non-convex? What do you think?
Also convex.
Also convex?
Yes.
Okay, yeah, absolutely true. All parabolas that point upwards are convex. So this is also convex, for example. This is also parabola pointing upwards. Okay. Yeah. Good. Good. So all of those are convex functions. Now, let us let us now look at this guy. Is this convex? And how you can or reason about it?
It should not be, right?
Should not be convex.
I think it will be convex.
But how can you reason about it?
That's half of parabola because we have strictly x more than 0.
It's not parabola though. A parabola is a second order function.
Half of. It's half
No.
of parabola.
No, it's not parabola at all because parabolas are quadratic functions.
Okay. If we look at x,
it looks like parabola, you mean, right? It's a
yeah. Okay.
It's a
So
polynomial.
we can look at square function and function of force that's middle and third. How it's stepping? I forgot.
Power.
Third power is just have no
Left hand
it
side.
have lesser than 0 in the left part, so it's will break convex function because if we take -5 and 5, it will be not convex. But if we remove the left side of this function, it will be look like x squared or x powered 4 function. So it's
true. Okay. So yeah, exactly. So you can see this function behave like visually. We're talking about visuals here. Of course, you can prove it rigorously, but you know, it'll take a little bit of work. Yeah, visually this is convex. And by the way, what is also interesting is that this function, which is x cubed, but on the negative half plane, this is actually concave, strictly concave. So this is strictly concave, right? And that one is strictly convex. Okay, sure. Convex function. We're not going to use this very often, though. X cubed convex, but we're not going to use it very often. There are reasons for this kind of thing. Okay, good. Convex multivariable functions. Just a few examples. Ax plus b. This is convex. Since it is linear, they're both convex and concave. So a convex function. This you know, this is the ellipsoid. Sorry, paraboloid. As long as h is positive semi-definite. Okay. By the way, this means positive semi-definite. You can say it means positive definite. Some people make a distinction between those, but in convex optimization, we never have strict inequality. So it is for us, it is positive semi-definite, not positive definite. Okay. So this h bigger than 0 is just means that eigenvalue symmetric matrix is strictly positive eigenvalues. This is paraboloid. So this would be the function. I'm not sure if I'll be able to draw it. Let me try, but something like this, and then something like this. Okay. So paraboloid. In n dimensions would be n-dimensional paraboloid. Okay. Okay. So when I draw it this way, sometimes it is difficult to understand what exactly I mean. What I mean is you have x1, x2 are in this direction, and in this direction it is f. So let me just write it. F in this direction, x1 and x2 are in those directions. So that is how you interpret this picture. Okay. Okay. Now, if the domain of optimization problem is convex, and the cost function is also convex, then it is called the convex optimization problem. So if the domain is convex, so where we look like the variables that are admissible, and the cost function, so what we want to minimize, is also convex, then it is called convex optimization problem. We, as I said before, always assume that the boundary of the domain is included in the problem. Okay. We can discuss strictly minimization problems, but in fact, doing maximization is no problem. It is just that when you minimize, you want the function to be convex. When you maximize, you want the function to be concave. Domain would always have to be convex. There is no such thing as concave domain. I'm not sure even how you would define a concave domain. It's something interesting to think about. But domain would always be convex. But for minimization, we want convex cost. For maximization, we want concave cost. Obviously, if the cost is linear, it is fine in either case. Okay. So that is what is called convex optimization. Key thing that we are going to study, that we are studying already. All right. There are very important properties of convex optimization problem. Okay. One, if the domain is not empty, there is a solution. So if the domain is empty, so you said, find me something, but here are restrictions, and restrictions are mutually contradicting. So you cannot find a single X which corresponds to your restrictions. Well, of course, then you wouldn't have any solutions. Makes sense. But if the domain is not empty, you would always have a solution. Somehow this is sounds a little bit trivial because yeah, sure, of course, there is a solution, right? But when you do it in practice, it is always nice to know that as long as you have a domain which is not empty, your solver will actually give you answer. If you did something like machine learning or other large-scale optimization things, you'll understand how painful it is to wait and then think, is there a solution to this problem? Is there something that can happen? Am I wasting my time? You know, this kind of thing. Here, in convex optimization, you can know for sure you would have a solution. Okay. Again, trivial, but nice in practice. More importantly, the problem doesn't have a local minima. So we can always find a path from any initial point to the solution, along which the cost function does not increase. Okay. So when you think about optimization in general, often enough what you are thinking about is something like a plane, I don't know, on which you have this huge plane. On which you have like, let me try to draw it nicely. You have something like things that stick out, things that upwards, things that stick out downwards, and this is kind of like how you will often think about optimizations. So what we really don't want is a situation where the function, let me even draw it simpler, I guess, in 2D. So you have a 1D, I guess, right? When you have a situation where you have a function which kind of slopes down, but then goes up, then goes to the optimum, and goes somewhere else. This is something you really don't want. Why? Well, imagine you are going, like you're starting here. Or you decrease, and here you'll stop because you cannot decrease any further. But somehow, in order to find the real minimum of the function, which is here, this is the real minimum of the function, you would have to somehow explore all of those regions, find that there is this decreasing region somewhere, somehow explore it, and go all the way down. How are you going to do it? I don't know. And that is a typical problem of general nonlinear optimizations. How do you find those things? So, typical and quite serious problem for optimization. For convex optimization doesn't exist. For convex optimization, you always have one and single global minimum. You don't have local minima. You can have like a stagnating region. Like, for example, convex optimization can have like a function, convex function can look like this. This is a convex cost function, and you can totally imagine that, let's say, like here is the same as here, is the same as here, so not very nice. So this is possible, right? What is not possible though, and this is quite interesting, not obvious, let me show you what is not possible. What is not possible is something like this. So why would it be bad? Well, let's say you're stuck here. You don't decrease anywhere. So it's very hard for you to know that there is a sudden decrease. And you could have went to this those better solutions if you only explored all the way until the edge here, right? This would have been very unfortunate. It doesn't have a local minima, but it has this kind of like plateau, then decrease. This is not a convex function. This is not a convex function. Why? Well, because here are 2 points, 1 point, another point. We connect them. The function sticks out. So not a convex function. For the same reason, this is not a convex function. Why? Well, because like take a point here, connect it to the point here. Some of the function sticks out, is on top of the line. So convex functions actually very nice. They are much easier to work with than general case functions. So that is the belief of convex optimization. All right. That is the definition. Now, in fact, though, this is not really how people understand convex optimization, which is kind of interesting. In fact, when people talk about convex optimization, people often talk about what Stephen Boyd liked to call disciplined convex programming or disciplined convex optimization. What is the difference between convex optimization and, sorry, between disciplined convex optimization and convex optimization? The difference is disciplined convex optimization is constructed out of blocks which we understand completely. So it's constructed out of blocks which we know how they behave, and for which we know how to work with them. So, for example, typical convex solvers will allow you to use this function, this function, this function, sorry, this function, this function, this function, this, and this. All of those will be allowed. Typical solver will deny you this function. Why? Well, because it doesn't know how, why? Well, because if you mess up the domain, so if you don't include this guy is not convex. And typical solvers don't like this kind of situation. They'll say, okay, not convex, so not going to use it. So often enough, what we call convex programming is building blocks, kind of like Lego, where you know each block will not mess up anything. That is why we typically work with those, but leave something out. The variety of functions that we work with is actually not very small. So there are norms, there are logarithm of a determinant, and other strange things, but not infinite. So not all non-convex functions can be represented. And that is important shortcoming. Okay. So for the material that we didn't cover last lecture, that is all. What I propose is we take a 5-minute break. Then we'll start the next lecture and we go as far as we can. Hopefully we'll cover the whole thing, but I don't know. So is it okay? Do we have time for a break? I think we do. We only had 1 hour, right? We'll take a 5-minute break and then we'll go 15 minutes more. Is that good? I don't see any approval or disapproval.
Okay.
Okay, good. Right. Right then. We'll see each other in 5 minutes.